Welcome everyone to parallel session number 3, where we'll be looking at different case studies. The first case study is an investigation into the impact of occupant-centric design method application on building energy efficiency and comfort. Caleb, if you'd like to start and present the first paper. Thank you.
Welcome everyone to the presentation of the paper titled Investigation on the Impact of Occupant-Centric Design Method Applications on Building Energy Efficiency and Comfort, a case study. My name is Zsófia Demebélafi, and with my colleagues Julia Simon and Edith Barna, we work at Budapest University of Technology and Economics. As an introduction, we can say that the ambitious goal is to be accomplished, is to have net zero energy consumption buildings very soon, and advances in building technology, construction quality, and design tools have been investigated vastly in the literature, but human needs are to be accounted for in a more thorough way during the design process, because without understanding and appropriately representing building occupants and their needs, it's not possible to estimate real in-use energy consumption levels. A research project was launched which assessed the current design practices of practitioners in the framework of an international project, the IEA EBC Annex 79, where a questionnaire was created for designers and professionals from different disciplines working in the construction industry. This survey included methods to consider occupants during their design process and also how users are taken into account by different design professionals. This survey was voluntary and anonymous. Let's have a look at the details of the survey. It consisted of 3 parts. Firstly, an overview about the respondents' current position, expertise, company size, and project types that they are working on. Secondly, the building user considerations were asked. And lastly, the simulation softwares and building user models were questioned. In Hungary, the survey was conducted in the autumn of 2021, and the total number of Hungarian responses was 36, and these were all fully completed questionnaires. The survey results here in Hungary showed that people working in planning and operation receives generally high percentage of data on future building use, but not that much on users. The number of building users, the preferred temperatures, and room functions are given as an input parameter for the designers, but behavioral factors and social background that might influence user behavior and also temporal variation of building use, let's say occupancy schedules, are given only in a very few cases. Survey results showed that here on this chart that in case of a company have more employees, let's say more than 50, then the number of occupants are more likely to be given as an input parameters. But on the small scale companies, they have more information most of the time about future occupants, for example, even demography of occupants. Our goal in this small-scale research project was to implement survey results into simulations and to find out to what extent the actual knowledge of occupant-related parameters could affect the design calculations. We chose a case study from Hungary. It's an office building, and we used Design Builder software to build up a simulation model. We set up simpler and more complex building occupant schedules, behavioral details like window or shading use. And also we established some structural comparisons to model a realistic decision-making situation in case of window glazing properties. The office building can be seen on these figures. It is located in Nyíregyháza, built in 2012 as a nearly zero energy building equipped with PV panels. The total heated floor area is 387.2 square meters, and it accommodates 10 occupants. 4 design cases were modeled. Version 1A and 1B had detailed occupant representation in terms of lighting, shading use, and also heating, ventilation schedules, and also some equipment, office and kitchen equipment schedules. 2A and 2B represented respectively, they were the simpler occupant representation models. In the end of this table, you can see that the difference between versions A and B is that they had different glazing properties, different window types, representing a design decision situation where the designer should make a decision whether a 2-layered window or a 3-layered window should be applied. On this slide, results of the simulation can be seen. An 8.4% increase could be seen in energy consumption levels between versions 1A and 2A, and a 9 and 5% increase in predicted yearly final energy consumption between the versions 1A, 1B and 2B. And in the end, when we looked at design decisions, a 9.9% increase between versions 1A and 1B. This is the effect of a design decision. And this was offset by only 1.1% caused by occupants compared to versions 2A and 2B. Let's have a look quickly on conclusions and future work. We could see that occupant representation may cause an 8.4–9.5% difference in annual building energy consumption in simulations. Also, an important message is that design calculation results supporting decision making should be carefully considered from the aspect of occupants. However, in this case, it was simulated that window type decisions was offset by only 1.1% by occupant representation types. Also, future work includes international survey results comparisons, which is going to be the next step of the international project Annex 79. So this survey was distributed and analyzed in many different countries around the world, and the next step in the next month is going to be compare the results internationally. Also, our team plans to conduct further case studies to investigate this phenomenon further. And with this, I want to thank you for your kind attention, and it's time for questions now.
Thank you very much. I really think it was a very interesting presentation, Zofia. I'd like to open the floor and let's use a chat room to see if there are any questions from the other members that are participating in the session. Perhaps I'll start. When I read through the paper, you also made reference to traditional design methods and the importance of traditional design methods and using, let's call it a user interface or a more focused approach on users and how they would in future utilize a particular building. Zofia, have you, the traditional design methods, have you done further research on that? And perhaps you can just briefly explain to us how do you see or what those methods are?
Yes, so with many colleagues internationally, we are working in Annex 79, not only in design decisions and the consideration of occupants during the design, but also how they use the building afterwards. So this is a new field, I would say, in research, which is called occupant-centric controls. It even have an abbreviation already, OCC. So if you can search for papers with this keyword, I would say occupant-centric controls, which considers more operation, then I think that's the way to move forward. Actually, it's not my field of expertise. I'm more from design, coming from an architectural background. So that's why I'm partly avoiding your question.
But I think as an architect, you must have an opinion on traditional design methods and how an architect should ideally interact with a client to ensure that the future use of the building moves closer to net zero. Do you have any particular views on that?
Yes, actually, it was very good to see that smaller studios, smaller engineering and design companies had a deeper look into occupant behavior, into future occupant behavior, according to the survey results. So ideally, a smaller group of people is working on a building with a more detailed knowledge on future occupants. That would be, I would say, the more traditional and more advanced or more beneficial way of design. But of course, I can understand that nowadays it's just a fairy tale sometimes if we design skyscrapers and we have no idea about the future occupancy. So it's a tricky question indeed. But thank you.
I think you've actually responded well. It depends on the size of the company, and if I understand you correctly, with smaller companies or a smaller number of occupants, it's much easier to get an understanding of their future behavior. I looked at the question and answer chat box. There aren't further questions. Perhaps Zofia, do you have any concluding remarks that you'd like to make?
Oh, no, thank you. I think I just give the floor to the next presenter. Thanks for your attention again.
Thank you. All right. If we could then have the program. Okay, so our next presentation focuses...
Good afternoon, everyone. So this paper that I'm going to present is about findings from a model calibration exercise of an experimental building which was used to test passive thermal comfort solutions. So the image here you can see is the experimental building that was used for calibration purpose. And this building is about 450 meters square. This experimental building in India uses, passive design techniques, and this was built as a prototype to test several technologies and operation practices where, the learnings can be applied for other buildings that will come up in the campus. The building wall assembly that were used in this building was CSEB wall with insulation. We also used ramp earth wall with insulation and AAC wall with insulation. This building is also heavily monitored in terms of indoor environmental quality, outdoor parameters, water, and energy. So since we were monitoring temperature and other parameters, we were looking at the data, and this is the graph that shows the monitored indoor and outdoor surface temperature of a west-facing wall of the experimental building. The lowest outdoor surface temperature, which is the yellow line in this graph, is about 14 degree, and the highest is 58 degrees Celsius. For the indoor surface temperature, which is the red line, is between 26 to 32 degrees Celsius, and it is very flat, as you can see. So it seemed that the insulation in this wall is effective because it is trying to maintain a constant temperature. However, we were not sure and we could not quantify unless we compared it with an uninsulated wall. So we wanted to address this issue by building a calibrated model of the experimental building based on the monitored data, and also to use this to test other passive solutions. So according to ASHRAE Guideline 14, the two commonly used metrics for calibration are mean bias error, which is MBE, and the root mean square error, which is RMSE. So for this exercise, errors were calculated for indoor temperature, inside surface temperature, and outside surface temperature. And since we did not have monthly energy data, we kind of looked at hourly data that was available to us. So a total of 720 readings were used to calculate the error. So here is the method that was followed. The building energy simulation model was built using Design Builder. The simulation model was calibrated in 4 steps, and simulations were run after each and every step, and the results were compared with hourly measured data. So the calibration exercise was done in a series of 4 steps to document the error systematically and also to understand the impact of each step in reducing the error. So the 4 steps were, step 1 was to collect design stage model for geometry, size, thermal properties of windows, door, roof, and wall construction assemblies, and also occupancy schedule. In step 2 was the correction of the lighting loads. The LPD, which was collected from the energy audit, was used as an input in the model. A very detailed energy audit was conducted for this. The lighting schedule was collected from the on-site surveys and interviews with the operations team. Similarly, in step 3, the correction of the EPD, which was collected from the energy audit, was used as an input in the model. And for the schedule as well, the on-site surveys and interviews kind of help for providing the input in the model. The last step, which is step 4, was the weather data correction. So in the previous first 3 steps, simulations were run with the typical meteorological year data, which is the TMY weather file. But for this step, we use the AMY file, which was developed, the AMY file was developed with the data from the weather station, which was located on top of the building. So when we looked at the results of both MBE and the RMSE, the errors, they were around 20% for the first 3 steps, as you can see in the graph, which shows that, correcting the design model for envelope and internal loads had a minimal impact. However, the MY weather data when we use the MY weather data, the reduction for the MBE and RMSE were significantly, to 13% to 17% respectively. And this demonstrated that the importance, how important, using actual weather file is for calibrating a model. While the RMSE was within the threshold, which is, which is below 30%, the MBE was 13%, that was achieved after step 4. And this was not within the acceptable tolerance. So further investigation was carried out for indoor air temperature and surface temperature data. So in this graph, it shows the measured and simulated indoor air temperature. We found that measured indoor air temperature for the unoccupied hours were higher than the simulated data. As you can see, the highlighted red area in the graph. The indoor air temperature was within 1 degree Celsius for occupied hours, but for unoccupied hours, it was around 4 degrees Celsius. So we conducted different scenarios like changing internal loads, envelope insulation, etc., to kind of match the measured data. And when we increased the internal load by 60%, we found the error reduced. But practically increasing 60% of the load was not true, and it was not true. So what we did is we conducted a thermal imaging survey of the interiors of the building to identify the source of internal loads. And this survey kind of showed that, the IoT box, which has a temperature sensor in it, was the source of heat. And this led to the discovery of, components inside the IoT sensor box that produce heat and affected the temperature sensor, which caused the readings to be higher with a constant profile. So we took another set of readings and compared with the IoT box readings with a hobo data logger. So here, as you can see, we found that, the air temperature, which was read by IoT box, is 3 degrees Celsius higher than the hobo data logger. So the orange line is the IoT box sensor and the yellow is the hobo data logger. So you can see around 3 degrees Celsius difference. So this result is similar to the temperature difference that was observed between the measured and the simulated results. So further, we also investigated the surface temperature data. It was also assessed to understand temperature differences between the measured and the simulated data. So we observed that there was no time lag between the air temperature and the inside surface temperature, which implies, a zero thermal mass of the wall. In the same data, when the outdoor temperature drops, which is the black line in the graph, there's no drop in the indoor air or surface temperature, which again implies, it is an extremely high thermal mass building. And these two observations were kind of contradictory. So when we went and investigated the surface temperature sensors, the surface temperature sensor props were cylindrical with only tangential contact with the wall, and the props were also uninsulated. So basically, the surface temperature were reading air temperature instead of surface temperature, and therefore there was no time lag that was observed in the data. So we could not use the air temperature and the surface temperature for calibration. However, uh, we collected another set of readings using hobo equipment for both air temperature and surface temperature for another week. And the simulation results for that week were compared with the hobo readings. So you can see the comparison in this graph. You can see that black and red lines are closer, which is the simulated and the hobo data, while the IoT box, which is the green line in the graph, has higher differences. So the MBE, so finally the MBE was achieved to 1% and the RMSE was achieved at 17%. So both RMSE and MBE was within the acceptable tolerance of according to ASHRAE guideline 14. So after the model was calibrated, we used the model for various purposes. It was we used the model to determine the value of insulation in terms of the thermal comfort that it provided. It was also used to simulate 3 wall assemblies. Each assembly was simulated with and without insulation. And the chart here shows the operative temperature in a naturally ventilated space for the rampart wall, which is plotted for one year against the adaptive thermal comfort band. So the blue dots is without insulation and the orange is with insulation. So you can see that the OT lies below the upper limit of the band, except for a few hours of the year for wall assembly without insulation, which is the blue dot. And with insulation, the space is about 3 degrees Celsius cooler. So we did similar analysis for other walls, which is CSEB wall and AC wall as well, using the calibrated model. The results for various wall assemblies that were simulated are summarized in this. We saw that, comfort hours are higher for without insulation wall, as highlighted inside a red box in this graph, because the OT values are less than the lower limit of the comfort band. And, given the climate, warming up and the potential of heat island effect in future, this analysis can now be conducted for future weather conditions using the model. With Also, with rise in temperature in urban areas in future, insulated walls will provide better thermal comfort. So the model was also used for life cycle cost analysis for insulated walls to discuss the value of the investment. It was also used for training a machine learning algorithm for predicting operative temperature. So to conclude about this paper, we calibrated an experimental building and employed it to simulate and analyze the thermal comfort of various wall assemblies. Mean bias error and was found to be 1%, and the root mean square error was found to be 17%. The calibration process showed the value of closer inspection of results, even if we meet the acceptable range, especially to build confidence among the non-researchers like CFO and for investment grade decisions. We also demonstrated in this paper the value of deep understanding of building physics to track down different issues with calibration. In this case, we observe a unique case where the simulated model data kind of help in identifying problems with the measurement equipment. And now once the model is calibrated, I think such a model becomes a powerful tool that can be used in multiple scenarios for improved operations, benchmarking, and future capital investment decisions. So thank you, and I am ready to take questions.
Thank you. That was really an interesting presentation. I don't see any questions on the chat box at the moment, but I would like to ask the different wall types. You've mentioned life cycle cost, but also if you compare the different wall types, which of these types do you expect to last the longest?
Hi, yeah. So I think that's a good question. So in terms of the three walls systems, which is AC and then rampart and CSEB, yeah, we did do the life cycle cost analysis as well as LCA, life cycle assessment. I am not sure which wall systems would last the most, but when we did the life cycle cost analysis, we did for mixed mode as well as fully conditioned scenarios, and in terms of the mixed mode building, we saw that the wall assemblies without insulation had the lowest life cycle cost, while if we were conditioning the whole building, we saw that insulation did play a vital role in terms of looking at the life cycle cost. And then we also did the LCA, which is the life cycle assessment. We found that rampart wall had the lowest impact in terms of both embodied emissions as well as operational emissions. Yeah.
Thank you, Amanda. I also I quite like rammed earth, and I've been exposed to it, and I agree with you. When we consider the emissions and the life cycle cost, it is a viable option to choose, especially given its thermal mass and the way that it protects or ensures a temperate indoor climate. Perhaps for the other participants, you can use at the bottom, there's a Q&A box. You can use the Q&A box if you have any questions. There are 2 more minutes. Are there any questions from anyone else? Okay, it doesn't seem as if there are any questions. I see we're 16 participants, but thank you very much, Amanda. Perhaps at the end of the session, we'll come back to the findings. It's a very interesting building, and it's quite commendable that on a university campus, these buildings are built as prototypes, and these prototypes are then investigated by the students. We'll move on now to the next presentation. Callum, if you could show us the summary again. So our next presentation is evaluating wind tower effectiveness in rammed earth buildings. And I think this also again ties up with the presentation by Amanda. I'm looking forward to this presentation. Thank you.
Hi, I am Zeynep Örgev. I am a graduate student at Kocaeli University. We conducted this study with Dr. Neslihan Türkmenoğlu Bayraktar. We are pleased to take part in this important event. Evaluation of wind tower effectiveness in rammed earth building. Today, with the effect of global warming, the increase in cooling requirements, even in settlements with more heating periods, increases the need for passive cooling systems. With natural ventilation, one of the most basic and effective passive cooling approaches, the need for mechanical system in cooling and air conditioning required to provide indoor climatic comfort conditions reduce and therefore energy consumption decreases. Natural ventilation components constructed to respond to the climatic conditions of the region where the buildings locate, meet the occupants' ventilation and cooling requirements, and come forward as significant elements that reflects the architectural identity of the district. Wind towers in regions with hot, dry climate characteristics are a distant example of this. Since the air flows from the outside to the indoor environment, air blocks with outdoor temperature also affect indoor temperatures. Because of this, from past to present, wind towers that allow the cooler air entrance in the elevations above the roof prevent the increase of interior temperature with outdoor temperature in hot, dry climate regions. The basic working principle of wind towers is based on the airflow stimulated by pressure difference due to buoyancy effect and forced convection by wind. Wind towers stimulate cross ventilation by catching upper cooler prevailing wind flows and orienting downwards to exit from the outlet openings located on the facade or roof. Air circulation also enhances the passive cooling of the occupants by increasing heat loss by convection from the building and body surfaces. Two-way wind towers have two circulation paths provided by opposite openings, one of which orients to prevailing winds. In the absence of wind, the need for ventilation and cooling is met by taking the hot air in through the tower openings during the day and cooling it out in the tower and expelling it out of the building openings. And during the night by taking the cool air in through the building openings and expelling the hot air from the tower openings. Wind towers are classified according to their opening direction as single-sided, double-sided, and multiple-sided. Versatile wind towers have a more complex system and are classified as X plus, H, I, and K types according to their plan layout. The rammed earth building, which is used in hot, dry climates, is a masonry construction system. The main material of which is soil, and a wall is built by compressing different moisted soil layers in a lateral forms between the temporary formwork panels and compacting it with the help of equipment to the built monolithic walls. Rammed earth buildings with widespread examples in the world have important potential in terms of aesthetics, durability, and energy efficiency. Adobe buildings constructed with soil bricks dried in the sun are common construction techniques in the cities such as Tunceli, Diyarbakır, Şanlıurfa with hot dry climate conditions. There are very few examples of rammed earth technique in Turkey. In this study, wind towers, one of the architectural approaches to natural ventilation systems, are investigated together with the rammed earth wall construction. The effect of wind towers, which are preferred in regions with hot, dry climates or on indoor climate comfort conditions, is evaluated with the Design Builder Simulation Program for rammed earth building models derived from wind tower alternatives with different opening locations under the climatic conditions of Diyarbakır. Thermal comfort levels achieved by the alternatives are compared with the result of the sample model made of reinforced concrete and without a wind tower. Diyarbakır is a city located in the southeastern Anatolia region with hot climate conditions, has similar architectural features to the Middle East region with fountains, pools for cooling by evaporation, courtyards, high walls, semi-open rooms for shading, massive outer walls for delaying and decreasing the peak heat loss in traditional residential buildings. Ramp-third buildings with wind towers for cooling effect by ventilation in summer can be constructed in newly built residential areas with small parcellation which does not permit courtyard design. An imaginary building is assumed to be in a low-rise residential area in Diyarbakır. A low-rise building with 3 zones with 6-meter, 12-meter dimensions is assumed to locate in the area in question. The opening area rate is 15% for each of the south and north facades of the building. The simulations are conducted for the zone in the middle interior. Interior doors are assumed to be closed for all simulations. 5 types alternative configuration with and without wind towers on the terrace roof of middle zone are generated for the CFD simulation process conducted with design builder program in order to present the natural ventilation and cooling performance and variation of thermal comfort sensation by Fenger methods for summer design day 21 July for the morning and afternoon hours. The alternative ARF concrete as the reference building is reinforced concrete building without a wind tower. The second alternative is a ramp-third building also without a wind tower. Primarily, the combined effect of natural ventilation building envelop thermophysical properties on thermal comfort investigated with the second alternative. The alternatives B1 WT ramps, B2 WT ramps, and B4 WT ramps have wind towers located on the middle part of the roof in the north with a different number of openings for each. The effects of the number of openings on thermal comfort conditions are investigated by these alternatives. The alternative C1WT ramps has a wind tower on the middle part of the roof in the south. The effect of the location of the wind tower is examined by this alternative. The effect of indoor airflow distribution and velocity on the variation of the operative temperatures. Accordingly, thermal comfort levels in the zone were compared for the 6 alternative situations. The homogeneous distribution of the air flows in the zone is provided most with B2 WT ramps according to the reference situation. The massive wall effect, which delays the sensation of the outdoor peak temperature effects in the indoor environment and also reduce the indoor temperature oscillations, could not provide a temperature decrease due to the ventilation carried out during the day with high temperature airflows. Although the PPD values were low in a few limited areas near the windows, they were rate of high throughout the place. Even with these alternatives. Although desired comfort temperatures are achieved in a limited area in front of the window, it's insufficient to provide climate comfort throughout this zone. Airflow distributions are provided homogeneously with all alternatives, even if airflows reach all parts of the zone for a models. A more effective circulation is obtained with B2 WT ramps and C1 WT ramps. For this reason, PME and PPD values are lower with these models. The interior operative temperature increase in the B4 WT ramps alternative depending on the increase in opening size. However, the same effect did not occur with B2 WT ramps with lower indoor operative temperature values by the effect of air velocities with lower temperature. Higher operative temperature and less air movement velocities are obtained at the point R in the indoor environment with all alternatives except B2 WT ramps according to the reference situation. The interior mean operative temperatures with all alternatives are above the comfort temperatures due to the size of opening, the transfer of hot outer air flows, and the effect of solar gains by closed windows. According to the analysis, the operative temperature values obtained in the reference and alternative models were insufficient to provide comfortable conditions during the warm periods. However, it is an appropriate approach to ventilate at night when the outdoor temperature is lower in hot climate conditions. When the applicability of the wind tower in hot climate conditions is evaluated within the scope of the study, it's observed that the wind tower has the potential to affect the comfort conditions positively in Diyarbakir conditions, and to meet the ventilation and cooling needs of the space to some extent when the openings are operated correctly. Therefore, the studies on these parameters have to increase. Thank you for listening.
Thank you for a very interesting presentation, Zanep. When I looked at the first wind tower, or you presented the first wind tower, it was quite an evocative structure. I was wondering, the craftsmanship and people who can build those structures, are they still available? Zanep, I think you're muted.
Yes. The main advantage of wind towers can be set to meet the ventilation and cooling needs without energy consumption, to be a traditional system suitable for hot, dry climate, and to strengthen the relationship established with the natural environment. Disadvantages are acoustic control, presence of dust and pollutants, and an uncontrollable source of wind.
Okay, thank you. My actual question is, do you still have people who can build those wind towers? Or there craftsmen or builders who are able to continue that tradition of building?
No.
Well, that's very unfortunate, because
No, there is no wind tower in Turkey.
Okay, I think as you've modeled, one sees the value of these wind towers and how, as a passive design measure, it can contribute to a built environment that does not consume resources unnecessarily. I've opened the chat box again, but I don't see any other questions. Zanep, perhaps from your side, any concluding remarks?
Can you repeat, please?
Do you have any remarks that you would like to conclude your session with?
No, thank you.
All right. Thanks then. Callum, if we could then show the program again to all the attendees. Our next presentation is focusing on net zero. It's a case study of the energy systems in an experimental building. Thank you.
Hello everyone, my name is Janani Venkatesh, and today I will be presenting this paper, which is a case study of an experimental building that is intended to be net zero, and whether its net zero goal was met across the evolution of the building. My co-authors in this paper are Prasad Vaidya, Amanda Thaunajam, Sanjay Prakash, Amit Chandra, Vismaya Paralkar, and Yashima Jain. So a 55-acre educational campus is planned to be constructed in Bangalore in India. It intends to be a digitally enabled, smart, and net zero campus. It will use passive design techniques and will have an operating system configured with IoT that continuously monitors its performance. In my paper, I have focused on an experimental building within the campus, which is a prototype to test different types of technologies and operation, and the learning can be applied to the larger net zero campus. So the experimental building was initially intended as a net zero office building with some workstations and a conference room. But later, a high energy consuming environmental lab and a kitchen were added. This increased the area of the EB to 470 square meters, as well as included some high energy consuming equipment. So the objective of this study is to track how the changes and evolution in the design, construction, and operation affected the net zero performance of the EB. And we've also seen how the learnings from this case study can be applied on other upcoming buildings on campus. The learnings may also be useful for other proposed net zero energy buildings. So the method we have followed is to analyze an experimental building based on 4 energy systems. That is the envelope systems, equipment and appliances, renewable energy system, and cooling system. And the net zero performance of these systems have been analyzed across 3 stages. That is the initial requirements of the project and the design response, the evolved requirements and design response, and learning from some post-construction studies that were conducted. So these are the 4 post-construction studies that were conducted in the EB: an energy audit, a life cycle assessment, a calibrated model and simulations, and a cost-benefit analysis. So in the next few slides, I will explain the evolution that the 4 energy systems in the EB underwent. So here in the envelope systems, there were 3 wall systems that were used in the building: compressed stabilized earth blocks with insulation, rammed earth with insulation, and AAC with insulation. So the building was initially a 287 square meter net zero energy building that used low embodied energy materials. But as the project requirements evolved and a kitchen and environmental lab were added, the area expanded. On the equipment and appliances front, the requirement from the beginning is to use energy efficient equipment and appliances and keep the loads at a minimum. So on the lighting front, LED lights and Bureau of Energy Efficiency star-rated appliances were used. So no changes on that front with the evolution. But on the equipment front, the lab and kitchen equipment such as VisiCooler, refrigerator, bain-marie, hot water kettles, etc. were added. And some equipment like the fridge and even the IoT servers needed to be operated all day. So this increased the equipment power density to 53.9 watts per meter square. On the renewable energy front, initially a 6 kilowatt peak solar PV array, a 14.8 kilowatt hour battery, and a 12 kilowatt inverter were installed to sustain the building during grid failure. But as there is increased energy consumption in the EB with the additional equipment, the PV capacity needs to be expanded. Also, initially net metering was assumed and excess energy was to be transported back to the grid. But as the experimental building is run on a temporary connection with the Bangalore Electricity Supply Company, we found that this is not possible. On the cooling system, the requirement from the beginning is to provide thermal comfort to the occupants using efficient and cost-effective methods. So initially, the entire building was to be air-conditioned, but later it was decided that the building would operate on mixed mode and many parts of the building would be naturally ventilated along with fans. So now in the next few slides, I'm going to highlight some of the findings from the post-construction studies. So in a life cycle assessment that was conducted to calculate the embodied carbon of the materials used in the EB, and it was compared with the standard case of brick. The study showed that the embodied carbon at the EB could be reduced by at least 52%. And for the best case scenario using rammed earth, it could even be reduced by 78%. A building energy simulation model was built and calibrated using Design Builder. When this calibrated model was compared with the baseline brick and plaster construction, the results showed that insulated wall assemblies alone reduced the operational energy by 11%. And the model also helped with some other findings like errors with the data collected by the sensors and also understanding thermal comfort in the EB. So I'll talk more about that in the next few slides. So this is an example of one of the errors that the model helped us discover. So we discovered that in one of the rooms, the air temperature was high and constant, while the calibrated model showed a lower temperature in the same room. So using a thermal imaging camera, it was found that the IoT sensor box itself produced heat, and affected the air temperature sensor. And this is why the readings were high and constant. Using data from the calibrated model, the operative temperature in a naturally ventilated space for 1 year was plotted against the adaptive thermal comfort band in the National Building Code of India. And it was found that the operative temperature for the entire year lies below the upper limit of the band, except for a few hours of the year. And this is without insulation. And with insulation, the space is about 2 degrees cooler. In a cost-benefit analysis that was conducted, it was found that the insulated walls had a lower life cycle cost if the building was fully air-conditioned, whereas a mixed mode operation showed a higher life cycle cost, and these are all for insulated walls. In an energy audit that was also conducted, the study identified some really high energy consuming appliances. For example, the kitchen had a bain-marie food warmer, and it was suggested that this should be replaced with insulated food containers. In addition, the energy audit also identified that the PV system needs to be expanded to support the additional loads in the building. So the main takeaways from this study are that long-term monitoring of a building helps in ensuring its net zero performance and also in identifying anomalies in the system. For example, we identified a 3-time battery discharge at night because grid power was coming in through the battery and not directly to the building. Another learning is that the EB, an experimental building, needs to be designed to be suited for experimentation. While we use the calibrated simulation model to compare for experimentation, an actual experimental design to compare with a base case is needed. So one of the things that were implemented in the EB are raceways that contain all the electrical wiring and conduits. As we experiment and the building evolves, there is no need to alter the envelopes to support the changes. Another learning is that unlike a numerical net zero goal that can keep changing with changes in building use and operation, the embodied carbon levels of the envelope are not affected and is much easier to achieve at the design stage. It would not require continuous tracking. On the energy front, understanding the loads and energy consumption patterns in the building can help optimize energy and tune back in to achieve net zero. Simulations and calibrated models can help optimize the building envelope, lighting, etc. in the design stage. And in the operation stage, they can provide benchmarks for energy consumption and optimizing the operation. Simulations can also help in detecting errors in the system. So overall, the experimental building proved to be a good testing ground for innovative approaches and technologies towards achieving net zero. And the post-construction studies have emphasized on the importance of conducting continuous monitoring across stages to ensure that the building is on track to achieve the goals. And these learnings will be useful while implementing approaches for the larger campus, as well as other proposed net zero buildings. I would like to thank my co-authors for their valuable contributions to this paper. And I would also like to thank the BSO conference for
Callum, I'm not sure whether we lost connection. The last part of Janani's presentation was a bit unclear. Could you confirm that we're still all online?
Yeah, all looks good on my end.
Okay, thanks. Then, Janani, I presume that you worked on the same building as Amanda. I'd like to confirm you made reference to the CACB and the round earth walls both being insulated. I wasn't 100% sure what the insulation materials were that you used. Can you explain that a bit more? And Amanda, you're welcome to assist.
Yeah, you're right that it's the same building that Amanda presented her study on. The insulation material that was used was XPS foam, and the building was super insulated, so all the wall systems were insulated. And the study that Amanda specifically worked on with the life cycle assessment as well showed that it was necessary for sort of a comparative building where there was no insulation, so that you can compare the embodied carbon in wall systems in both buildings. And that's one of the important findings in the study, that an experimental building needs to be designed for experimentation.
Do you think a wall, a round earth wall that actually has a slow flywheel effect to transfer heat from outdoors to indoors, do you think it's really necessary to have additional XPS insulation in a wall like that?
So that's the study that was conducted using the calibrated simulation model, where the temperature difference in an insulated and an uninsulated wall were compared, and it showed that there was a 2-degree difference in the insulated building. So it did make a difference in terms of the temperature.
Okay, and then I'm also interested in the IoT, and Amanda also earlier mentioned the nearly 4 degrees Celsius difference. Do you think that the instrument itself is the only reason, or are there other reasons? Because in Amanda's presentation also, it seemed as if it's a relatively small instrument that could have such a huge effect on an entire...
Right. So Amanda's study measured sort of different sort of factors that could contribute to the error in the simulated model and the actual building. But the location of the sensor itself was at a place where the sensors were not placed across the room, so it was sort of difficult to know if the temperatures were different across the places. But where the sensor was placed, it was sort of measuring the the heat from the sensor itself contributed to the the increase in temperature. But I think it's worth looking at different parts in this same space itself.
Okay, so the IoT was measuring itself then. Sort
of, yeah.
Okay, thanks. Thank you for the presentation. Is there anything else that you'd like to tell us about the building? Because it looks like quite a unique building.
Nothing else, just that the learnings were great, and the level of data that's being collected with the IoT system and the different sensors that are measuring data on an everyday basis gives us so much insight into how a building could be made efficient, and how energy could be optimized in the building. So if this is sort of scaled up across the campus, it could be a really sort of a learning for other proposed net zero buildings in India and other countries in the global south.
Okay, when was this building originally built?
So currently it's just an experimental building, and I think the construction itself has happened in the past 2 years, but the larger campus itself is being planned.
And then is the building occupied at all at the moment?
It is occupied. As I mentioned, it was intended as a workstation. So people they have laptops and they sort of do their everyday office work in the experimental building. And there's also a kitchen where food is cooked, and the occupants consume food as well. And other than that, there's an environmental lab where there's experimentation going on, and IoT work as well.
Okay, thank you very much.
Yeah.
Thank you, Jamani. It was a very interesting presentation, and I think well with the work that Amanda was doing. I'd like to go to the chat box. There was an earlier question, and I think it was directed to Zaneb's presentation. And the question refers to PPD being perhaps a more relevant parameter for mechanically controlled environments, as opposed to OT being solely looked at for the study, considering that there were no local control methods. Zaneb, I saw you starting to respond to that. I'm not sure whether you'd like to share the response with the rest of the panel.
Thank you for the question. An evaluation was made on the operative temperature. In addition, we used PPD values in this study as they reflect the user's experience with the comfort of the environment. Thank you.
Okay, all right. I think we can perhaps continue the conversation after our last presentation. Kellum, if you could share the program, I think we're on time. So our next presentation is now focusing on data-driven investigation, looking at thermal comfort in an informal settlement, and specifically looking at a case study in Mumbai. I'm really interested in the informal settlements. I'm looking forward to the presentation. Thanks.
Hello everyone, I'm Divya Chaudhary and I'm going to present my topic, data-driven investigation of thermal comfort in an informal settlement, a case of Mumbai. Today, more than 50% of the world's population resides in urban areas. The above world map shows the booming urbanized cities in red. Informal settlements are a common sight, especially in emerging economies. 1/3 of the population of the world lives in informal settlements. In case of India, the highest number of slum households are seen in Maharashtra state according to the census of 2011. Mumbai has the highest percentage ratio of slum households to total urban households amongst the metro cities in India. Every ward has its total population to slum population represented in the lower graph. Administrative Ward S of Mumbai is where most of the 50% of the total population lives in the informal settlements, and this is also the location where the current study has taken place. Most informal settlements are only striving on natural ventilation. This research aims to study the impact of environmental parameters along the personal parameters of behavior on thermal comfort in these informal settlements. Thus, indoor thermal comfort is necessary to be studied and investigated. Thermal comfort is a condition of mind which expresses the thermal satisfaction and is assessed by the subjective evaluation. Our skin interacts with the environment in various ways, which results in change of core temperature in different scenarios. Factors such as air temperature, relative humidity, airspeed, mean radiant temperature, clothing, metabolism are important parameters of thermal comfort. For indoor comfort, in the case of naturally ventilated building, ASHRAE 55 suggests the adaptive comfort model against the PMV PPD method. Moving to the methods used, CB comfort tool, which helps in checking the compliance with the ASHRAE 55 adaptive comfort was used. To study the annual thermal parameters, Design Builder was used to simulate the conditions. This study was taken place at Shivnagar at Bhandup in the city of Mumbai. After the research area of informal settlements and thermal comfort was identified, the secondary data helped in forming the research structure. And by looking at the methods of studying the thermal comfort in informal settlements, the primary data was collected through indoor field readings inside the two houses of the same settlement. Later, the base cases were formed with the current housing conditions on the Design Builder software. The month-wise average operative temperature was obtained through the results of simulation. Retrofit solutions were researched through the fair conditioning program developed by C-Balance Solutions and simulated over the base case to arrive at conclusion. Located in the suburb of Bhandup in Mumbai, the settlement is surrounded by few industries and high-rise complexes. This informal settlement has a cluster of around 100 houses. 2 houses were selected for the study. House 1 is a two-story chawl located on G+1 floor. The house 2 is situated on the ground floor. Its side and rear walls are shared by the other houses in the settlement. Here are some photographs of the houses. Out of all the materials, the roof had the maximum surface temperature of 42 degrees inside the house. Even in house 2, the maximum surface temperature was observed on the roof with 35 degrees Celsius. Mumbai being warm and humid city with higher temperatures and humidity observed during summers, it became important to simulate the structures to see every month's result in thermal comfort. A model was built on Design Builder for each of the house. From 8 a.m. to 6 p.m. in house 1, the occupancy is of 1 member. Rest of all the hours, all 4 members are present. In house 2, it was unoccupied from 10 a.m. to 4 p.m. as all the members were working. 4 hours had 1 member occupancy, while the rest of the hours had full occupancy. Materials of the both houses were same as the semi-pakka, that is the walls made up of bricks and the roof made up of tin. In the simulation results, we can see as the driver temperature has risen, the air temperature, mean radiant temperature and operative temperature followed its trend. The highest operative temperature was observed in the month of May and lowest in January. After plotting the operative temperature against the outdoor temperature, all months except January and December were uncomfortable. February was near to the comfortable range. For house 2 simulation results, the operative temperature reached 34 degrees at its peak and the lowest at 28 degrees in Jan. The monthly average of relative humidity was more than 80% from June to September. After plotting against the operative temperature and outdoor temperature, all the months except January and December were uncomfortable. Since majority of the months are observed to be uncomfortable, strategies need to be applied to reduce the thermal stress. As seen in the previous data, the highest temperature was observed from the roof. Since there is a less scope for renovation due to the monetary assets, retrofit solutions are explored. These are the type of solution used for simulating over the base case. They were selected with the principles of heat transfer, radiation, insulation, etc. with the help of air conditioning programs, which are currently identifying the retrofit solutions for installation of the installation over the informal settlements. The first solution was alufoil. The coating of aluminum foil with its low emissivity of 0.01, due to which shiny surface prevents any radiant heating. The foam inside acts as an insulation. Second are the reprocessed Tetra Pak sheets that are made from recycled foil-lined beverages containers. Third is the rooftop gardening, which can be built up by the locals. It works on the principle of radiant heating and insulation. PET bottles. Since water has the highest specific heat capacity of any liquid, it can absorb a lot of heat and make the thermal lag. All of the solutions are low cost except rooftop urban gardening. Gardening and water-filled PET bottles are heavyweight solutions. They have to be tested properly before installation. Gardening will require energy to function for irrigation. The irrigation factor adds to the cost. Considering the species and maintenance, the cost can increase. But for the PET bottles, the maintenance can be an issue if the water stagnates and needs to be refilled. Alufoil and Tetra Pak sheets have low maintenance and can be secured over the tin roof with some joinery. For the next set of solutions, dormer window. Here a vent is created over the tin roof. A curved chimney structure can be created over the vent to prevent rainfall from entering into the house. The entry of the window was also faced against the direction of the wind and rainfall in the model. The idea was to create a draft and ventilation in the house where the windows of the house will be facing on the windward side and the entry of the dormer window will be on the leeward side. Only solution here which can address the high humidity levels. This solution also provides daylight. This was tested by the Mahila Housing Seva Trust in Gujarat. Fiberglass insulation works on the principle of conductive heat transfer. This is a thick layer which provides insulation. Modroof is a company-based solution, and its availability can be an issue with in other parts of the country due to its transportation factor. All of these three are lightweight solutions and no maintenance. The materials were simulated and here were other results. In the month of May, which is the hottest month in the city, fiberglass insulation and alfoil showed reduction in operative temperature. Same was done for house 2. In the month of May, fiberglass showed the best performance. But considering all month averages, the performance of alfoil gave the best results. This is the graphical representation of house 1. Showing the reduction in the operative temperature, which is seen in fiberglass insulation. Second one was alufoil, and the third best performance was seen in Tetra Pak sheets. In case of house 2, alufoil has the most reduction, followed by Tetra Pak sheets. To sum up, all design cases have shown reduction compared to their base cases. Rooftop urban gardening, mod roof, PET bottles, Tetra Pak sheets showed reduction in summer months and increase of operative temperature in winter months. They can provide comfort in both seasons, but comparing the balance of all aspects such as cost and maintenance, as well as the performance, alufoil and Tetra Pak sheets and fiberglass insulation gave the better results. Coming to the conclusion, changing the orientation and redesigning the settlements at the same place is not possible in an informal settlements, except options such as redevelopment. There are limitations in informal settlements because they are formed considering the other factors such as better economic opportunities, better connectivity to their workplace, and ensuring livelihood rather than focusing on the quality of life. Studying thermal comfort is important because it affects the day-to-day life and productivity of the occupants. The women residents are usually the 24 occupants and do strenuous activities which produce heat and increase thermal stress. Thus, a closer look has been taken to improve their thermal comfort and as a parameter of living condition by studying the built environment. Here, the roof is exposed compared to the walls, as the households are densely packed and the walls are usually shared. Materials become an important part of the intervention for the roof assembly. Thus, the current existing settlement retrofitting indoors is a way to enhance the quality of life by mitigating the thermal stress in these settlements. Thank you.
Thank you, Divya. It was an interesting presentation. The roof retrofits are a unique way to address indoor comfort levels. What type of ceiling structures are being used currently, or is this simply a roofing material and there's no ceiling on the inside of the occupied rooms?
Yeah, right. There's no ceiling made up of concrete, such as they are only made up of tin, which were observed in these settlements. Most of them were made up of tin, that is the corrugated sheet. So that's the, yeah.
So it's only the thin material of the corrugated sheet.
Yes, and the structural members. That's it. Yeah.
If you do a retrofit then of a rooftop garden, wouldn't that not have a structural implication on how you're going to solve the heat gain then?
Yeah, definitely. Rooftop gardening becomes a complicated issue because even the weight of the soil, that is also a problem. So for that, structural reinforcement has to be done. And in a tropical climate like Mumbai, at least 15 centimeters of soil would be required. So that would also become an issue, and hence that is why I had categorized it as a costly solution.
I saw that. And then the PET bottles were also quite an interesting solution. Is it something that is being done at the moment or not?
Yes, after this research was conducted, there were live experimentations done by the same organization, CPC Balance, with whom I worked. So they had also installed the water-filled PET bottles over the roof. Even for that, we required the structural reinforcements because now one bottle, we used 1 kg of bottle. So around the roof area might be around 100 square feet. So imagining like 200 kgs of bottles over that roof is a complicated thing. So that is why even structural reinforcement was used in that case also.
Okay, no, I understand. Yeah, in South Africa, we have another method. We struggle with a similar challenge where we only have the corrugated roof sheeting, but then once you have an air gap and you install a ceiling underneath that, it leads to quite a reduction load, and it's a low-cost solution that is also lightweight. And other benefits are that dust, for instance, doesn't come inside the rooms as easily as what it would have previously.
So those bottles aren't, they are air filled basically.
Okay, yes, this is a ceiling board similar to the roof sheeting, but it's a flat sheet that is installed then on the inside of the rooms, but an air gap is left between the roof sheeting and the ceiling board. Okay, I see there are no other questions or comments. I'd like to open the floor. Any questions or comments on the presentation that we just had from Divya? Okay, and then our previous presentations, Sophia, on looking at occupant-centric design approach, Amanda, who with Zinani looked at the experimental building on the campus, Zanep focusing on wind tower effectiveness, and then Divya on informal settlements and how roof insulation could lead to a more temperate indoor climate. Perhaps I would like to facilitate a conversation in this regard because I see recurring themes. The one is passive methodologies. The one is occupant behavior and how do we behave or how do we design for people who will use a building which we perhaps as architects design or as modelers predict future users. Are there any comments from the presenters on these themes that I've observed? It doesn't seem as if in the chat box there are more comments. So I'd like to thank you for the presentations today. At 3:15, there will be a debate on whether modelers are indeed literate. And I think this is a really important question because the modelers ultimately predict the future optimization and even cost of a building and also the longevity of a building. So please join us at 3:15. But before we go, I'd like to again thank Callum for ensuring the smooth running of all the technology. Thanks, Callum. I really appreciate your efforts. And then goodbye, everyone. I'll see you then at 3:15. Bye-bye.